Very happy to have him. It's Simon Cotter. And there's the talk title, A Constrained Approach to the Simulation and Analysis of Stochastic Multiscale Chemical Kinetics. Take it away, Simon.
Thank you very much, and thanks very much for the invitation. Thanks to the organisers and for the whole programme. Oh yeah, I need to turn on my microphone. That should be working now. Okay. So I'm going to talk about some work that originally came about when I was in Oxford, and it came out from a paper originally working with these three mathematicians here, two of which are in the room. So both Radek and Kostas are knocking around somewhere, and I believe that Yanis is going to come along to the programme at the end of May. So originally this paper that we looked at, we were looking at the diffusion approximation of slow variables in multiscale systems, but the work that I'm going to present now is newer work based on this same approach, but with different results. So here's a quick outline of the talk. First, I'm going to give an introduction, and basically this work is about improving the approximations that we can make, that we would make if we did the more standard quasi-steady state approach to multiscale chemical kinetics. So we saw a little bit about this in Tom's talk when he was looking at the Michaelis-Menten kinetics. So I'm then going to describe this new approach, which is this constrained approach, and then I'm going to also look at what happens when we want to apply this approach to a really complicated system. We can do this in an iterative nested approach. And then finally, if I get time, and I don't think I probably will, I might show how this same approach can be used to increase the accuracy of ODE approximations of multiscale systems. Okay, so I'm going to sort of skim over this introduction part because these things have already been talked about and will be talked about many times in the rest of the week. But really, we're interested in the biochemical processes that occur in a cell where the concentrations of some of the species in the systems are relatively low, and that means that stochastic fluctuations in the dynamics of these systems plays a key part in those dynamics. Okay, so fortunately there's a wealth of literature on how we might, for example, be able to simulate such a stochastic chemical network. So for example, we have the Gillespie stochastic simulation algorithm, and I'm hoping that most of you are familiar with this, but for those who are not, I'll quickly run through this. So the idea is that we have a set of M chemical reactions, each of which has associated with it an intensity or a propensity or a hazard function which tells us how frequently this reaction should be firing. So the first step in the algorithm is that we compute these propensities for all of the M reactions. We then compute what will be the waiting time to the next reaction, and that's given by an exponential random variable, and we can compute that here. And then we decide with probability proportional to each of the propensities of those reactions which reaction has actually taken place. That's in step 3. And then we update our state vector dependent on the stoichiometry of that particular reaction that's fired, and then we just rinse and repeat. And this is a way that we can simulate trajectories of these stochastic chemical networks. The problem is, though, that a lot of these chemical networks are inherently very multiscale. And what I mean by that is that there are some reactions in the system which are occurring many times on a time scale for which other reactions are unlikely to fire at all. So here we have an example of such a system. This is a very simple system with only containing monomolecular reactions, but I've picked the rates such that these two reactions, reaction 2 and reaction 3, are firing many times on the timescale for which other reactions are firing. So we can see that this is the trajectories that we get when we run the Gillespie SSA for this particular system, and we can see that species X1 and X2 are subject to a lot of reactions, so they're changing very frequently, and the species X3 is changing less fast. This is a slow variable. So the problem here is that we're simulating every single reaction in the system, and what we really want to do is to understand the effective dynamics of these slow variables, this X3, or alternatively X1 plus X2, without the need for the simulation of all of these fast reactions. Okay, so what we want to do is we want to approximate the dynamics of this full system by some effective dynamics. So what we want to do is remove these fast reactions so that we don't have to simulate them anymore. And now we can approximate this network by this network, where S is the slow variable x1 plus x2. And we need to compute this effective rate K4. Now the problem here is that the actual rate of this reaction firing is given by K4 multiplied by the amount of x2 we have in the system. But in the reduced model, we're not modeling the amount, we're not keeping count of how many molecules of x1 and x2 we have. We're only modeling what S is doing, which is this x1 plus x2. So these multiscale methods are concerned with how do we compute what this effective rate should actually be to best approximate the dynamics of this full system. Okay, so the natural thing that most people do is to apply the quasi-steady state assumption. So I have a quick summary in my own words. People may probably disagree with how I've summarized this, but the philosophy of the quasi-steady state assumption is that the fast variables are changing on such a fast timescale that we can, the rates of the slow reactions in comparison are negligible. And that means if we want to work out what the expected amount of x2 is in the system, given a particular value of S, which is what we need in order to compute this effective rate K4, then all we need to do in practice is to look at the invariant distribution of those fast reactions completely in isolation. So let me go through an example to explain exactly what I mean here. So here we have what is the most simple multiscale system that you could possibly think of. Okay, so we have two species, x1 and x2, and we have four reactions. x1 is being created here. Then these two reactions, reaction 2 and reaction 3, are concerned with x1 quickly changing between x1 and x2. So these reactions are occurring on a faster timescale to either this reaction or this reaction where x2 is decaying. So what we want to do is to approximate the dynamics of the system by an effective system where instead of keeping count of both x1 and x2, which are fluctuating wildly, we want to approximate that by the dynamics of this slow quantity S. So for this particular example, the slowly changing quantity in the system is the quantity which is invariant with respect to the fast reactions. So if we take S is equal to x1 plus x2, then these two reactions don't change the value of S at all. Okay, so this is our slowly changing variable in this system. So now, if we're doing the quasi-steady state assumption and we want to approximate what this effective rate K4 would be, we need to look at this system, the fast subsystem, which is given by these two fast reactions completely in isolation. So note that we need to do this for each value of S because this system maintains the value of S. So if we run either of these reactions, S never changes. So for each value of S, we need to understand what's going on in this system in order to compute the effective rate of this reaction here. So in the quasi-steady state assumption, we only look at this fast subsystem. Okay, so the nice thing about this example, which is why I've picked it, is that we can analyze everything exactly, including the invariant distribution of this fast subsystem. So this is just a system which contains only monomolecular reactions, and so that we can find the invariant distribution, which is given by a binomial distribution, and we can work out what the parameters are in that distribution by solving the steady state solution of the mean field ODE. So we arrive at this binomial distribution, which is got a rate given by K2 over K2 plus K3. So now what we want to do, the reason why we've computed this invariant distribution of this fast subsystem is we want to compute what the expected rate of that fourth reaction is going to be. So that's exactly what we're doing here. We want to compute the expectation of this, the propensity of our fourth reaction, given that our value of the slow variable is this value of S. So this is, because we know the invariant distribution of x2 is in this fast subsystem is a binomial random variable. We can very easily compute this expectation, and so we arrive at this value, k2, k4, s over k2 plus k3. So we can plug this back into the effective system, and we arrive at the following thing. So we now just have a simple birth-death process for the slow variable s, with birth rate given by k1, which just comes from the previous system, and then this rate here of the death, which is the effective rate that we've just computed, which is given by k2, k4 over k2 plus k3. So one thing that we could do if we wanted to quantify the error in the approximation that we've made using this quasi-steady state assumption is to look at the invariant distribution of this effective system and compare it with the invariant distribution of the slow variable in the full system. Okay, so that's exactly what we're going to do here. So if this is a birth-death system, and we can very easily find the invariant distribution for this system, and it's given by a Poisson random variable with intensity given by k1 times k2 plus k3 over k2, k4. So this is the approximation that we get using the quasi-steady state assumption. This is a very simple system, so in fact we can find the invariant distribution of the full system very easily. It's a Poisson random variable with intensity k1 over k4 for x1 and intensity k1 times k3 plus k4 over k2, k4 for x2. So we can marginalize that now and compute what that distribution looks like for the slow variable s, and that gives us this as what the true invariant distribution of the slow variable should be. So it's a Poisson random variable given by this intensity here. Now you can see that this intensity is different from the one that we got from the quasi-steady state assumption, and that's because of errors that we've incorporated due to the assumption of this large separation of timescales between the fast and the slow reactions. So the error that we're getting in the Poisson intensity of this particular system is given by k1 over k2. Now you'll notice that k1 is the rate of the birth of x1 or s, and so we've already said that this is a slow reaction. And k2 is the rate of one of the fast reactions. So we can see that this error, if we were to increase the difference in timescales between our slow reactions and our fast reactions, this error would converge to zero, which is great. So in the limit that we have very, very fast reactions and very slow reactions, the quasi-steady state assumption is exact. But one thing to bear in mind, so actually in a multiscale system, all that we're saying is that the propensity of the slow reactions is much smaller than the propensity of the fast reactions. So for example, if we look at the expectation of the propensity of reaction 1, which is just k1, divide that by the expectation of the propensity of reaction 2, well that's given by k2 times x1 bar, where x1 bar is the average value of x1 in the system. So even if this is much less than 1, i.e. we have a multiscale system, feasibly k1 over k2 could still be order 1 or even bigger, depending on how big our value of x1 bar is. So even for highly multiscale systems, the quasi-steady state assumption can still give us considerable error in our approximation of things such as the invariant distribution. So in order to try to improve these approximations, I'm going to present to you the constrained approach, which is essentially a correction to the quasi-steady state assumption, which leads to a better approximation of the effective dynamics. Oh, that should say the constrained philosophy there. So the constrained philosophy is much the same as the quasi-steady state assumption. We still assume that the fast variables are entering equilibrium on a time scale which is negligible with respect to the rates of the slow reactions. But there is a difference, and that difference is that we don't assume that the slow reactions have no effect on the distribution of the fast variables. So in fact, in a lot of systems, the slow reactions can actually change the fast variables, and in that sense they are also changing the distributions of those fast variables. And if we don't take that into account, then we incur the sort of errors that we saw in the previous example. So what does that mean in practice? Well, it means we have to do a little bit more work than the quasi-steady state assumption. We can't just look at the fast subsystem. What we actually need to do is constrain the dynamics of the whole system to a particular value of the slow variables. So we're going to allow all of the slow reactions to run because they too can affect the invariant distribution of the fast variables. So this is a little bit hard to express in words, so I'm going to go through this again in an example. So the idea is that we take a system of m reactions, and they have reactants given by nu1, nu2 up to nu_m, and they have products given by nu1 dashed up to nu_m dashed. So this here represents the stoichiometry of the full system. So one thing that we need to do, which is very important, is that we need to pick a slow variable for our system, or slow variables, depending on how what we want to do. So these slow variables, we can pick these reasonably easy. We look at the stoichiometries of the fast reactions, and we simply pick vectors which are perpendicular to the stoichiometries of the fast reactions. So in other words, the slow variables are not going to be changed by those fast reactions. The next thing we want to do is we want to form a basis for the full state space, which includes this slow variable s, and we're going to just pad it out with a set of fast variables which gives us a basis for the full system. So I'm going to define this thing called the constrained stoichiometric projector. All the projector does is it takes a state of the system with the slow variable equal to s and the fast variables f given in this vector here, and all it does is it projects the value of the slow variable to 0 and leaves all of the fast variables unchanged. So what we're going to do is we're going to apply this stoichiometric projection to each of the reactions in our system so that we can ensure that none of the reactions now change the value of the slow variable, but they still allow the fast variables to change. So the reason we want to do this is we want to understand what the invariant distribution of the fast variables is given a particular value of the slow variables s. So we're essentially putting a pin through the value of our slow variables and saying, we're not going to let this change, and now we're going to let all of the other reactions take place and see what happens to the fast variables. So we apply this projection to each of our stoichiometric vectors. But the problem is that sometimes we can come across reactions which are no longer follow mass action kinetics, and which could, in theory, lead to negative values of some of the chemical species. So we also multiply each of the propensities in the system by an indicator function, which ensures that once we add on this stoichiometric vector, we're still in the positive quadrant of the state space. So because of this projection, the value of the slow variables can't change at all, and we're just interested in how the fast variables are going to change. The important thing here is that this system now gives us a way to approximate better the invariant distribution of the fast variables given the slow variables, which it does a better job than the quasi-steady state assumption. So once we've created this system, we can do a number of things. We could simulate it, which would be expensive still, or we can use analytical results, which I'll talk about a little bit later on, or we can create the generator for this particular system and find the invariant density through the null space of the generator. So I'm just going to talk very briefly about the generator, so that if we were to put the chemical master equation into vector matrix form, then we'd get this, so dp by dt is equal to g times p, where p is the vector of the probability that we're in a particular state. So if we find the null space of this operator g, then we can find the invariant distribution of the system. And the great thing about this is this means that we don't have to run any expensive stochastic simulations in order to approximate this invariant density. We can find it directly numerically. Okay, so I'm just going to go through the exact same example that I did before with the quasi-steady state assumption, but now with this constrained approach. Okay, so again, these two reactions here, just to remind you, are very fast. So we've got these these happening many, many more times than either reaction 1 or reaction 4. So the first thing we need to do with a constrained approach is to construct a basis for the state space made up of slow and fast variables. Well, we know what the slow variable is. It's given by s is equal to x1 plus x2, and that's because it's perpendicular to the fast stoichiometries of these two reactions here. We can then pick our fast variable to be either x1 or x2. So you do get slightly different approximations depending on which of the fast variables you choose, but usually it doesn't matter too much. In this example, it does slightly matter for reasons that I won't go into now, but we're going to choose preferentially the fast variable to be equal to x2. So now that we have a basis for our state space, we can define this projector for this particular example. So if we're in a state x1 plus x2, we want to find the point in the state space where s is equal to 0, but our fast variables are still equal to what they were here. So our fast variable was equal to x2, so we don't want to change x2, so we let x2 be equal to x2. x1 is decided by the fact that we want our slow variable to be equal to 0, so in order for these things to sum to 0, we need to set x1 to be equal to minus x2. So now what we're going to do is we're going to apply this stoichiometric projection to all of the reactions in the system, and I'm just going to go through those briefly one by one. So the first reaction, we've got x1 coming from the empty set. We've just got this birth process of x1 being produced at some rate k1. Okay, so we're going to apply our stoichiometric projection to the stoichiometry of this particular system. We're creating x1 out of nothing, so our stoichiometric vector is given by 1, 0. And when we apply the projection to that, we get 0, 0. So that means for the constrained system, this reaction has no overall effect on the state space when it fires. And that means we can just get rid of it. Okay? Now, reactions 2 and 3, they're very similar. They don't change the slow variable in any way, and that means that when we do this projection to them, it doesn't alter these reactions at all. So these reactions are completely unaffected by this projection. The interesting bit comes when we look at this fourth reaction, R4. So here we have x2, which remember is the fast variable, decaying at some rate, k4. So the stoichiometric vector for this reaction is given by 0, minus 1. And when we apply the projection to it, what we get is 1, minus 1. So this is the new stoichiometric change for this reaction. And that means effectively that this reaction is changed to x2 turning into x1 at rate k4. Now this seems really weird, and when I show this to people, they usually say, what on earth are you doing? This doesn't make any sense. But hopefully it'll make a bit more sense when I show you the results, why it's worth doing this. Okay, so the constrained subsystem is largely similar to the one that we got from the quasi-steady state assumption, except instead of this rate of x2 going to x1 being k3, we've now got two reactions which have got that stoichiometry, so we can add their rates together, so we get the rate k3 plus k4. Now, as we did before, we can find the invariant distribution of this subsystem. It's a binomial distribution, and it's got this mean here, k2 over k2 plus k3 plus k4. So we can, in exactly the same way as we did before, compute the expectation of the propensity of the fourth reaction, given that we're at a particular value s in the slow state space. And that's given by k2, k4s over k2 plus k3 plus k4. So this is our effective system. And as we did before, we can compute the invariant density of that effective system in order to compare it with the true invariant distribution of the slow variable. So this is what we get for the constrained approximation. And in fact, you may or may not remember, this is exactly what we got for the true system. So the constrained approach here gives us an approximation of the invariant density of the slow variable, which is exact. So here's a picture to bring all of that information together. So the yellow histogram here is the distribution that we get for the slow variable when we look at the full generator, the full system. The red dashed line is the invariant distribution of the slow variable with the quasi-steady state assumption, and then the constrained generator is given by the blue line. And the blue line and the yellow histogram line up exactly. But this was just an incredibly simple linear system, so I want to try and persuade you now with a more complicated nonlinear system that this works for more interesting examples, although this is still relatively simple. So we're going to look at this system here. So we've got two chemical species again, X1 and X2. This time they're undergoing 7 different reactions, and we have 2 types of bimolecular reactions. We've got interactions between X1 and X2, and reactions with X1 and itself. Okay, so this system is interesting because in certain parameter regimes we have multiscale properties of this system, in that reactions 5 and 6 are occurring more frequently than the other reactions in the system. And this is also an interesting example because this ends up with a stochastic switch. We end up with the invariant distribution of this particular example being bimodal. So we have some more interesting behavior in this second toy example. So just to show that, on the left-hand side here, I've got a log plot of the invariant distribution of this particular example. So we have 2 modes, one here and one here. So if you look at trajectories, we'll spend some time here, and then we'll switch up, and then we'll come back down again. On the right-hand pane figure here, I'm trying to show how multiscale this system is. And in fact, I picked a parameter regime for this example so that it's not highly multiscale, but that reactions 5 and 6 are the most frequent in the system. So what we're seeing here is the ratio of propensity which is due to those fast reactions. So at 1, all of the reactions are the fast reactions. At 0, all of the reactions are the slow reactions. So we can see that depending where we are in the state space, it changes from around 0.5, it goes a little lower than that, closer to the origin, to around, in this region where we're likely to spend a lot of our time, around 80% of the reactions are due to the fast reactions. And in fact, we can compute the expectation of this ratio by timesing these 2 things together and integrating, and you get that we expect the expected amount of the fast reactions in the system in stationarity will be around 70%. Okay, so I'm going to go through the analysis both using the quasi-steady state assumption and using the constrained approximation. Okay, so these are the 2 fast reactions, and so with the quasi-steady state assumption we assume that we can find out everything we need about the invariant distribution of the fast variables by only considering these 2 fast reactions. Okay, so we've got our slow variable. It's a slightly different slow variable this time because we've got different stoichiometries in our fast reactions, and the slow variable here is given by x1 plus 2x2. So this quantity doesn't change when either of these reactions fires. Okay, so if we wanted to look at the constrained subsystem, we'd want to pick, so first we create a basis for our whole system, and we've picked our fast variable to be x2, and this then helps us to define this stoichiometric projection, where this example is given by minus 2x2, x2. So when we apply this, I'm not going to go through the details for each of the reactions this time, but when you apply this projection to each of the reactions, we arrive at this subsystem, which again is similar to this system up here, but we have a different rate. We have a different rate for this reversible reaction. Here we have K6 plus K7. So all I'm going to do at this stage is to compute the expectation of all of the slow variables to work out the effective rates, and then create this effective dynamics of the slow variable S. And then we're going to look at the invariant distributions of these different approximations. So this slide is very much like we saw before for the linear example, except it's for this bimodal example. So we're looking at the invariant density of the slow variable x1 plus 2x2. So I've got 3 different graphs here. One is the approximate full generator. So this system is simple enough that I can truncate the state space of the full system and try to approximate very accurately what the invariant distribution of the full system is. I can then marginalize, and that's how I arrived at this yellow histogram. We then have the QSSA approximation given by the red dashed line, and the constrained approximation given by the blue line. So there's a big increase in the accuracy for the approximation of this effective system using the constrained approach rather than the quasi-steady state. So this is a table just summarizing that information. So although the quasi-steady state assumption allows us to accurately find the left-hand peak in the bimodal distribution, you can see that it's way off for the right-hand one, and also the relative peak heights are very wrong compared with the true density. So we can see here the, yes, yeah.
But here you have chosen the parameters such that the QSSA is not valid anymore. So
exactly, yeah. But the important thing is that the constrained approach always converges to the quasi-steady state as that rate gets bigger. So the point is that if you want to try to apply one of these approaches and you're not sure that there's a huge scalar difference, it doesn't matter, because if there is a big difference in timescales, then the constrained approach will give you something very similar to the quasi-steady state. But you're exactly right. I have picked this example, and I'm not shying away from it, to show the differences between the two approaches. Okay, so once we've done this, once we understand these these approximations of the effective dynamics of this slow variable, we can do a lot of things that we can't do for the generator of the full system. So through this multiscale reduction, we can hugely reduce the size of the state space, and we also remove this stiffness in the system due to this multiscale property. So we can do things that we can't do with a full generator, and I'm going to give some brief examples. A brief example of one thing that we can do. So there are the methods attributed to Fernhead and Sherlock, who are at Lancaster, which is an exact Gibbs sampler for sampling paths of Markov modulated Poisson processes conditioned on their endpoints. But this can be a very, very expensive thing because it requires the calculation of the exponential of the generator for the system, and also powers of the generator for very large R, which will become full as R gets big. So this is something that you just can't consider doing for a system with a large state space, such as a multiscale system. But what we can do is we can use the effective generator that we approximate using the constrained approach in order to approximate these paths. So for instance, in that bimodal system, we can now sample paths which start in one of the modes and end at the other in a time scale of t is equal to 10. So we can sample paths that we know are going to make a transition, which might be useful in situations where we want to understand the dynamics of large deviations. So this is just a heat plot of lots of those trajectories. So we're seeing that all of our mass starts here. We enter stationarity around here, and then one by one the trajectories move to this higher mode. Okay, so just checking how much time I have left. Okay, so I'm probably not going to get onto these ODE approximations, but if anybody's interested in how you can use these constrained approaches to make more accurate ODE approximations, then come and talk to me later today. Okay, so I've shown how we can reduce the system in a particular way where we have to find this invariant distribution of this constrained subsystem. But what happens if we're in a situation where the constrained subsystem or the fast subsystem is itself very large and multiscale? Then we still have a problem. We still need to find the invariant distribution of this fast subsystem or the constrained subsystem. So one method which is talked about in this paper by Eric van den Eyden and D. Liu and Veen and E. It's called nested stochastic simulation algorithm. And essentially what they're doing is they're nesting quasi-steady state assumptions so that they can reduce the complexity of their reduced system. So if they apply enough quasi-steady state assumptions, eventually they end up with something which is very easy to deal with. So if we have multiple timescales, what can we do? And if we have multiple timescales, that often means that the constrained subsystem or the fast subsystem is itself very difficult to deal with. So here we can imagine this is a relatively simple system, but we've got kappa, which is the rate with which x1 and x2 are switching between each other, and that's much faster than the rate that x2 and x3 are switching between each other, but that is still much greater than the rates of these slow reactions. So we have 3 different timescales occurring in this simple system. So if we were to apply the quasi-steady state assumption, what would we do? Well, first we would take all of the fast reactions out of the system and try to find the invariant density of that system. So here we've ended up with 4 fast reactions, but this is itself a highly multiscale system. These reactions are occurring on a much faster time scale than these ones. So that might mean that it might have a large state space, and there might be a large difference in time scales. But what we can do is we can apply the quasi-steady state assumption iteratively to this second system, and that means we end up with only the fastest reactions. So now what we need to do is to understand this system, to understand the relative quantities of x1 and x2 in this system. Then we analyze this system in order to find the relative quantities of x3, and then we can understand the rate of this last reaction here. Okay, so we can analyze this system very easily, as we have before in this talk. It's just a binomial distribution, and we can work out the expectation of the value of x2 given particular values of the slow variables. So we can then plug that back up into our first subsystem. We've replaced the first 2 sets of reactions just by this slow variable S2, and we can plug in the expectation of S2 given S1 into here so that we get an effective rate of gamma over 2 for this first fast subsystem. We can compute the invariant density of this again, and that finally goes up to the effective dynamics, and that leads us to this effective slow system for S1, which has rate K1 and rate K2 over 3 for this for the death process. So again, we could look at the invariant distributions in order to quantify the error in our approximation using the quasi-steady state assumption. So if we look at the invariant density of this system, we get S is a Poisson random variable with intensity given by 3K1 over K2. If we look at the invariant distribution of the full system with slow variable S1 given by x1 plus x2 plus x3, then we arrive at this intensity here. So what we should notice is that these 2 intensities agree in the limit that both gamma and kappa go to infinity. We end up with this 3 gamma k, k1 over k2 times gamma kappa, so the gammas and kappas disappear, all the other bits become very, very small, and then we arrive at this. But what if we wanted to have something more approximate that worked not in the limit of those 2 things being huge, but in a more realistic scenario where it's somewhere where they are happening more frequently, but not so infrequently that we don't need to worry about the slow reactions? So the constrained approach can be applied iteratively in exactly the same way that quasi-steady state assumption can be. So we can find our slow variable, which is given by x1 plus x2 plus x3. That's invariant with respect to all of these 4 fast reactions. And we choose our basis by filling our fast variables with x2 and x3, because both of these things are changing very, very frequently. So this defines our projection that we're going to apply to all of our reactions. And when we apply that to all of our reactions, we end up with this system. So if we look at the difference between this system and the full system, we see that, like the example previously, we've lost our first reaction, and our last reaction is changed from being a death process to x3 changing into x1. But this is itself reasonably, well, it's not complicated because it's linear, and I've picked that so that we can do nice analysis on it. But if it was non-linear, then it would be very complicated. But this is a multiscale 2-dimensional system. So what we're going to do is we're going to apply another set of constraints. We're going to have a second slow variable. This time, this slow variable is invariant with respect to the fastest reactions in the system. So we're setting our slow variable to be equal to x1 plus x2. We only need one fast variable this time because we have still this additional constraint that x1 plus x2 plus x3 remains constant in this system. So we've already reduced a 3-dimensional system to a 2-dimensional one. I'm now going to do an additional constraint which is going to lead to a 1-dimensional system. So we end up with a second stoichiometric projection, and when we apply that to the system, we arrive at the following system that we need to understand. So this is an example where once we apply the projection, we end up with system which does not follow mass action kinetics. And you can see that because I've had to multiply, so the rate of this reaction x2 is given by kappa x2 plus k2 x3. But feasibly, if x2 was equal to 0 and x3 was non-zero, then we could still lose a molecule of x2 even though we don't have one. So that's why we need to add this multiplied by this identity function here, which ensures that x2, this reaction will only fire when x2 is bigger than 0. So this has non-mass action kinetics. That could be a problem, but we can still construct the generator for this system and find the invariant distribution of this system by finding the null space of that generator. Or we can use, one thing that we can notice is that this system is weakly reversible and has deficiency 0, so that we can apply the results of Anderson, Karakian, and Kurtz to find this product form of the invariant measure of the system. So I've just written this out, but essentially we can use these results to find the invariant distributions for rather weird non-mass action kinetic systems. And that means now we can compute the effective rates of all of the slow reactions in the system. That is, we're modeling this system by an effective system which is just a birth-death process. And we can compute the invariant densities of these different approximations. The yellow histogram is again the invariant distribution of the slow variable that we get from the full system. The red dashed line is the QSSA approximation, and the blue line is from the constrained approximation. Okay, I have 2 minutes. I'm going to quickly run through this. So essentially, you can apply these same approaches to models of ordinary differential equations. And I appreciate this meeting is about stochastics, which is why I've just kind of slipped this in at the end. So consider, for example, this system here, which is a system approximating the dynamics of enzymatic reactions. So we have an enzyme reacting with a substrate to make a complex. These reactions are very fast. And then that complex can either go back to being this, or it can change that substrate into the product, and so that we end up with the enzyme and the product. Now, normally, it's assumed that this last reaction, this reversible part of the reaction, doesn't happen. But it is possible for, in reality, an enzyme and a product to come together and become a complex again. So one way to do this is to apply Michaelis-Menten to compute what the expected value of the complex is given particular values of xe and xs. So if we were to do that, then we arrive at what should be reasonably familiar Michaelis-Menten rate, and then we can write down an ODE approximation of the rate of production of xp using this approximation. So we can also notice that the number of xs and xp together are a constant, and also the total number of enzymes, which is the total number of enzymes plus the number of complexes, are constants, and so we arrive at this equation here. So I'm now going to show you how we can apply the constrained methods to this system. So what we do first is we take the full system and we apply the constrained projector exactly as I have showed you for the stochastic examples. And when we do that, we arrive at the following constrained subsystem. So in order to compute the expected rate of the production of xp, we need to know what the expected value of xc is given a particular number of enzymes and substrates in the system. So we can do that by finding the complex equilibrium of this system, and we're going to denote that by cc. So then the constrained approximation will give us this ODE here. So we're using the complex equilibrium that we get from this constrained subsystem instead of the quasi-steady state assumption fast subsystem. And then we arrive at this ODE here. So these are the solutions of these ODEs. And this time I haven't picked the parameters to show how brilliant my method is. These are, I can't remember the exact name of the chemical species that I got these reaction rates from. But anyway, this is a more realistic example. So I'm showing you the value of the product as it changes in time between time 0 and 1,000. For the full model, which is the thing we want to approximate with a one-dimensional model, through the Michaelis-Menten kinetics and through the constrained kinetics. Now you can see by eye they're all reasonably close, but if you look at the top end, you can see hopefully that the orange line is slightly above the other two. We can see this a bit more clearly when we take the difference between all those lines, and in fact this is actually relative error in the production of XP. So here we have the Michaelis-Menten error, and here we have the constrained error. In fact, actually I only got my ODE solver to work at a relative error of 10 to the minus 10, so I'm not entirely sure how low this would go. This is only numerics that I've done in the last week or so. But you can see that you can end up with a more approximate, a better approximation of these effective dynamics even in ordinary differential equations system approximations. Okay, so I'm probably running slightly over, so I also want to show, I've got an advert on my last slide which I want to show, but these are my conclusions and these are my references, and this is a shameless workshop plug. I've got a workshop on multiscale modelling and inverse problems for stochastic reaction kinetics in Manchester in August, and registration will be going live next week. Some of the people who are in this room are going to give talks on this as well, so please do register and come along. Okay, thank you.
A few questions, and then I have a few announcements. So, Romain is first.
Yeah, thank you. Very clear talk. I was wondering what would be the computational cost of computing the invariant distribution or the moment, in a non-linear, typical large system. So, I don't know, 10 species, you have to compute the moments of the first species.
Okay, so that depends on the system. So far I've been mainly looking at sort of toy models, and it can be fractions of a second. It depends really on the method that you're using to find that invariant distribution. If the constrained subsystem is weakly reversible and zero deficient, then you can just write it out. You don't even need to do any computations. It's a bit more expensive if you need to do it through the generator. That really depends on the size of the state space, so that's going to be entirely problem dependent. But essentially you're trying to find the zero eigenvector of that generator. You need to take into account the cost also of creating that generator as well. But compared with stochastic simulations, I mean, it's not even worth comparing. They're just so many orders of magnitude difference. But that's something I want to do. I want to apply this now to more interesting, like oscillatory systems and things like that, higher order, more complex systems, to see if this is going to scale up.
So in your examples, the slow variables cover all the species. So like a positive linear combination of all the species is one of the slow variables. So when you fix the numbers, fix the value for the slow variable, it's essentially a closed system. So you have a finite generator matrix, so you can find the invariant distribution.
Yeah.
But in cases where it's an infinite matrix, where your slow variables do not cover everything, then you probably have to use some kind of truncation.
Absolutely, you need to
and pile up as you proceed through time.
Exactly, so that there is definitely a point at which it's not accurate or feasible to use this generator method, in which case you'd have to again switch to stochastic simulations of your constrained subsystem, or some other approximations in order to find that invariant distribution. But that's a good point, yeah.
Yeah, I want to make sure I understand what you're calling the quasi-steady state approximation.
Yeah, sure, yeah.
You're computing a distribution that does not depend upon the value of the slow variable?
No, it does depend on the value of the slow variables. So, for example, let me go up to one of the examples. So, here, for example, okay. So this is our fast subsystem from the quasi-steady state assumption, and we've got these reactions here, and it does depend on S, because S tells you the total number of particles in there. So you would need to compute that for every value of S in order to work out the effective rates.
Okay, maybe one more quick question. Just a small question. I mean, on your very first example, and you were comparing you're computing the error in the mean of the Poisson distribution that you got from two approaches. So you were actually, you were characterizing it as just the absolute difference. I'm wondering why you didn't consider, like, suppose one rate was 100, the other was 103. You might say 3 is not small, but the relative error had more to do with K4 than K1 over K2. So I'm just wondering why you chose to characterize the error in that way.
Okay, so let me just find, oh yes, this slide here, yeah. Okay, so it's kind of weird, and it's, the error only depends on K1 and K2.
The absolute error, but the relative error is something to do with like K4 over K2 plus K3.
Oh, I see, yes, that's true. So if I was to divide this by this, then I get something different. In fact, it would be K4 over K2 plus K3. Yeah, you're right, actually.
Is the reason that you care more about the K1 over K2 than that error? Is there a particular reason for that?
No, that's a good point. I mean, I could definitely look at that. The reason I do this is because you can see that this error in absolute terms can be big even when there's a large difference in scale. But I agree, maybe it's unfair of me not to talk also about the relative error in that as well. I agree, yeah.
Okay, let's thank Simon again.